All right, let's talk about one of my favorite parts of trigonometry, verifying identities. Now, I know it can feel like you're staring at a really tough puzzle, but what if I told you there's a kind of master key, a single strategy that can unlock almost any of them? Well, there is, and today we're going to learn how to use it.
So, here's what we're going to cover. First, we'll get a handle on what this identity puzzle is all about. Then, we'll go over the rules of the game. After that, I'll give you that master key strategy. We'll use it to unlock some proofs, talk about common traps to avoid, and finally, see how this all connects from the classroom to computers.
So, what does it actually mean to verify an identity? You're not solving for X here. Think of it more like you're a detective. You have two expressions that look totally different, and your job is to prove, without a doubt, that they're secretly the exact same thing in disguise. And here's the official take on it. We're showing that two things are equal for all possible angles. That all is super important. It's why we can't just plug in, say, 30 degrees and call it a day. We have to use algebra to transform one side, step by step, until it looks identical to the other side.
Now, like any good game, there are rules. And these aren't just suggestions. They're the core principles that make sure your proof is actually valid. If you break these, you're not really proving anything at all.
Let's break these down. Rule number one, and this is the big one, you can only work on one side of the equation. Why? Because if you start moving stuff across the equal sign, you're basically assuming they're equal from the start, which is the very thing you're trying to prove. It's a logical trap. Next, always start with a side that looks messier. Trust me, it's way easier to take a complicated thing and simplify it than to take a simple thing and try to build it up. Okay, and that brings us to the star of the show, your master key. While there are lots of little tricks you can learn, this one strategy is so incredibly powerful that it just works time and time again on a huge range of these identity puzzles.
And here it is, 3 simple steps. First, you pick that more complicated-looking side. Second, and this is the magic part, you replace every single function, whether it's tangent, secant, whatever, with what it equals in terms of sine and cosine. And third, you just do the algebra. You simplify, you cancel, and you watch as it transforms into the other side.
All right, enough talk. Let's actually see this master key in action. We're going to walk through 3 different proofs, from pretty basic to a little more advanced, and you'll see how this one strategy just cuts right through them. Let's start with a classic. We need to prove that tangent of theta times cosine of theta equals sine of theta. Okay, pretty clearly the left side is the more complex one, right? So that's our starting point. Now, we use our master key. We replace tangent theta with what we know it is, sine theta over cosine theta. So now our expression is sine over cosine times cosine, and look at that, it's set up perfectly. We have a cosine in the denominator and a cosine in the numerator. They just cancel each other out.
And what are we left with? Just sine theta, which is exactly what's on the right side of the equation. And boom, identity verified. See how clean that was?
Okay, let's level up a little bit. This time we've got cotangent, sine, and secant all multiplied together, and we have to show that the whole thing simplifies down to just the number 1.
No problem. We just use the master key again. Cotangent becomes cosine over sine. Sine, well, it's already sine. And secant becomes 1 over cosine. Now just look at what we've created. The sine on top cancels with the sine on the bottom. The cosine on top cancels with the cosine on the bottom. Everything pairs up and cancels out.
And we're left with just plain old 1. The left side magically became the right side. So even with more pieces to the puzzle, the strategy holds up perfectly. 2 for 2.
All right, time for the advanced round. Now, this one looks a little intimidating, right? We've got a fraction, we've got addition. How on earth is sine squared over cosine plus another cosine going to turn into secant? Let's just trust the strategy.
So before we can simplify, we need to combine these two terms. And to do that, we need a common denominator, which is obviously cosine theta. That gives us sine squared plus cosine squared all over a single cosine. And right there, that should set off bells in your head. Sine squared plus cosine squared, that's the most famous identity of them all. It equals 1. So that whole complicated numerator just becomes the number 1. And now we have 1 over cosine theta. And what is 1 over cosine? Well, it's secant theta. We did it. We took that messy left side and proved it was just secant theta in disguise. Identity verified. Okay, now that you've seen the right way to do it, let's spend a minute on how things can go wrong. Honestly, knowing what not to do is just as important as knowing the strategy itself. This is it. This is the number one mistake I see students make all the time. It is so tempting to just start moving things across the equal sign the way you would in a normal algebra problem. But you just can't do that here. Remember, it breaks the entire logic of the proof. You have to pick a side and stay on that side. So just to hammer it home, the big pitfalls are working both sides at once. That's that circular reasoning trap, and starting with the simpler side. It's just so much harder to figure out how to make something more complicated in the right way. Stick to simplifying. So you might be thinking, okay, that's a neat mental puzzle, but why does this matter? Am I ever going to use this in real life? And the answer is absolutely. This kind of logic has some incredibly powerful applications. Think about the powerful software that engineers and scientists use, like MATLAB or Mathematica. When they plug in some ridiculously complex formula, the first thing the computer does is try to simplify it. And how does it do that? It uses algorithms built on the exact same rules we just used. It often translates everything into its own version of sine and cosine to find the simplest, most efficient way to solve the problem. And that kind of leaves us with a pretty cool final thought. When you learn to verify these identities, you're not just learning math for a test. You're actually learning to think with the same kind of rigorous, step-by-step logic that powers so much of our digital world. So the next time you see one of these puzzles, remember, you're not just solving for theta. You're learning the language of logic itself.